So the difference between the amplitude of one energy and the amplitude of the other energy is the integral of the derivative of the amplitude with respect to, say, S. And that derivative brings down an extra powers of momentum in the denominator, makes the integral finite. And so it really makes sense that you can compute the difference of something without knowing what the thing is itself, because you don't understand the fundamental physics at very short distances. On the other hand, you can measure the amplitude at one, and then you can predict what it should be at another energy. And it may be that one can recast the whole business of renormalization theory in these terms. And that would be quite nice. That's not quite what we have in the formulations that I've seen. Instead, there's always a cutoff, and then then we do some algebra with the cutoff, in which the algebra really doesn't make any sense because the cutoff is infinite. On the other hand, if you instead are only computing differences of things and assuming that the things themselves at some energy or scale will be things that you measure, then you might be able to do the whole thing honestly with no infinity showing up at all. So that's, if any of you know of a treatment of renormalization that follows that procedure, let me know. Because it would be, oh damn it, I've got to go get my reading glasses. Okay. So basically, I'll be following along in Schwartz's treatment here. So we saw in phi cube theory, and this was typically massless phi cube theory, the one loop amplitude in which we were doing basically this was minus g squared over 32 pi squared log of q squared over cutoff lambda squared, where here q squared is minus p squared, and we're going to be thinking about values of p such that p squared is negative. And the reason for that is, this is of course after, well, we'll be using Pauli-Villar's regularization, so we can think of that's a Pauli-Villar's regulator there. Anyway, the lowest order amplitude for some process might be this. We're looking at a T-channel scattering, and in fact, one of the things that we're going to be working toward is the change in the photon, basically the change in the amplitude due to the exchange of a photon. In other words, the corrections to the Coulomb potential. And but here we're still in scalar phi cube theory, and so we imagine some particle goes along, the phi cube goes across, and then the one loop correction to that process would be the one that we were just computing last time. And so this process here would be IG squared, and then I over P squared, where P is this momentum. And the analogous thing here would be IG squared, I over P squared, I, the loop term, and then again I over P squared. So the I over P squared is this part and this part, and then the IG squared give you these two vertices. So we're basically looking at this part of the diagram and then this part of the diagram, and that's why P squared is negative. And if we combine these two terms, then what we would get would be I m of Q, say, would be, m0 plus m1, and this would be IG squared 1 over P squared times well, sorry, I should have written what this is. That's what I meant to write here. This is IG squared 1 over P squared times minus G squared over 32 pi squared, then log minus P squared over lambda squared, and then again 1 over P squared. And so then if we combine the two together, what we get is G squared over Q squared, 1 minus 1 over 32 I squared, G squared over Q squared, log Q squared over lambda squared, plus perhaps higher terms when we go higher. So this is our M of Q being the sum of this amplitude plus that amplitude. And now, let me remind you that in 4 dimensions what we have is d cubed x dt, that's the action, and then we have the action density. And for a scalar field, we would have something like phi dot squared. Okay. So what does that mean from the point of view of dimensional analysis? Well, this is L cubed t phi squared over t squared. And of course, I'm talking in terms of natural units. And so L and T are the same. And so this is actually basically L to the 4th over L squared. So this is L squared phi squared. This means that the dimension of phi should be mass, because then we would have that this would be L squared m squared. And that's 1, because the dimension of mass is 1 over the dimension of length. In other words, the Fermi is 1 over 140 MeV, say. On the other hand, in phi cubed theory, and of course everything here has to have dimension 1, because it's action. And in phi cubed theory, then we have integral d cubed x dt g phi cubed. So this has to have dimension 1, but that means we have L to the 4th from these guys, g. This is m cubed. So this means that LG has to be 1. And so that means that the dimension of G is also mass. Normally, coupling constants are dimensionless, and for phi 4 theory, the coupling constant is dimensionless, but in phi cubed theory, the coupling constant has dimension of mass. So what Schwartz does is he defines a G tilde in this way. G tilde squared is G squared over Q squared. Now that will be dimensionless. And so we have dimension of G tilde is 1. And so now this M of Q is G tilde squared times 1 minus G tilde squared over 32 pi squared log Q squared over lambda squared r. Now, of course, what we're going to do is we're going to say G tilde squared renormalized will be defined as M, the actual M at some energy scale, energy scale Q0. And so that means GR is M of that, and that would be then this, which is G tilde squared minus G tilde to the 4th over 32 pi squared log Q0 squared over lambda squared. Okay. Now, all right, so we have a formula here which says G tilde squared is that plus that. And we can invert that, and we can get G tilde squared then is G tilde squared renormalized plus it's plus G tilde to the 4th over 32 pi squared log Q0 squared over lambda squared. Just wondering, did I make a mistake here? That is that. All right, let's leave that. Let's instead imagine that we're going to expand G tilde squared in the power series in GR squared. And so we'd imagine it would be like that, although there's a bit of a swindle going on here. In any case, if we say G tilde squared is this plus that, then we can substitute that in there, and then we would get a formula for M of Q. And this would be, so we're substituting into here. The first term is G tilde squared R plus 1 over 32 pi squared G tilde squared R log Q 0 squared over lambda squared. So this whole thing is that term there. Then the next term is minus 1 over 32 pi squared G tilde R plus 1 over 32 pi squared this is a 4. G renormalized to the tilde to the 4th log Q0 squared over lambda squared squared and then squared. That's this term. Okay, at that point, expanding just to order G to the 4th, what we get is this, and then we get this term and that term, and we ignore that term. And because that would be the order, the coupling constant to the 6th term. And so that gives us G tilde squared renormalized plus 1 over 32 pi squared G tilde to the fourth renormalized. And then if I write it somewhat redundantly, okay, I've got a problem here because one of them is Q. Oh, yeah, I forgot here. Log Q squared over lambda squared. And so this is log Q squared over lambda squared. And so this then is G tilde squared renormalized plus 1 over 32 pi squared G tilde to the fourth renormalized, and now it's log of Q0 squared over Q squared. Okay. And as I said at the beginning of this, is a question? As I said at the beginning, I think the best way to do this is to instead say we're just going to compute m of q minus m of q0. That will be some integral of a derivative with respect to q, or if you want q squared, which would be easier. So we compute m of q. In other words, if you computed m of q squared minus m of q0 squared, then you would have some sort of an integral of a derivative, an integral dq squared of some derivative dq squared of this amplitude. And this derivative would be finite, would be a finite integral, and so this thing would actually make sense. Whereas doing it the way Schwartz and others do it, and I'm not blaming Schwartz because this is the way it is in essentially all the textbooks, we always have this cutoff, and it seems to me it makes no mathematical sense at all. I've just never been a fan of it. I've always hated renormalization. But on the other hand, doing it this way, where you actually have finite integrals, this makes sense. And as I said, it would be nice to redo renormalization theory entirely in terms of integrating finite quantities. And then, of course, you would say this is something we measure. Okay. All right, well, let's go on with the phi cube theory. Let's first of all just remind ourselves that something like this with a p here and, of course, a p there, we found that this was effectively, after the Feynman trick, the Pauli-Vallaz regulator. It's this integral 0 to 1 dx log m squared minus t squared x1 minus x over lambda squared. Okay. So now what we're we're sort of, we're going to jump now from phi cubed to scalar QED. And scalar QED is, I don't know, Schwartz thinks of it as simpler. I think of it as more complicated, because the complications are that you have a more complicated action, you have worse divergences than in spinor QED. What's more complicated in spinor QED is, of course, you've got these gamma matrices, so when you go to do traces, you have a problem. But that's just an arithmetic problem. All right, anyway, let's do scalar QED. So what we've got then is a photon, and then we've got a loop. Here's P, K, K minus P, photon goes along P, and this turns out to be minus IE squared integral d4 K d pi to the fourth, and now we have I over 2K mu minus P mu over K minus P squared minus M squared plus I epsilon, and then I 2K nu minus P nu over K squared minus M squared plus I epsilon. What's going on here is that these vertices, the vertex, you remember, that has two scalars and one photon has a derivative in it. The derivative acting on the scalar field. And that's why we have these extra factors of K minus P. However, because it's the scalar QED, we also have this diagram. So this is PP, and this simply is K, and so this is a very divergent diagram. It's 2I E squared G mu nu, and then it's an integral d4 K 2 pi to the fourth I over K squared minus M squared plus I epsilon. So this is quadratically divergent, and that leads to all sorts of problems. Here, if you didn't have the derivative terms, you have only a log divergence, but you also have in principle a quadratic divergence here from the K squared term. Okay, so what we have then is I pi mu nu. So this is what you get when you combine these together, and then you get something that's d4 K 2 pi to the fourth, and now a big so this is rather complicated. All right, that's the numerator. And I guess here's the denominator. Okay. All right, well, what we know from Lorentz invariance that this has to be delta 1 of P squared and M squared P squared G mu nu plus delta 2 of P squared and M squared P mu P nu. And well, to tell you the truth, I'm not sure why we can't have a G mu nu term in there without a P squared. But I suppose you can rewrite delta 1 as more of a P squared plus something else. All right. Now, before going further, let's make a definition. This is the photon propagator. A mu x, a mu y. This is again in scalar QED. So it's time-ordered product the vacuum of this supposed to be. I think this is really, well, all right, if we're pretending that this is the fully interacting theory, then that would be the real vacuum. E4 P, 2 pi to the fourth, e to the I P, x minus y, I G mu nu of P. And this thing is called the dressed propagator. And dressed, I guess, means that we're talking about the real field and the real vacuum here. And to lowest order, in Feynman gauge, Ig mu nu, so that's mu nu of P, is minus I, and again I'm using, here I'm just, instead of changing all the g's to eta, I'm just going to leave them as g. This g, of course, is 1 and minus 1, minus 1, minus 1. Over p squared plus I epsilon. This is in Feynman gauge. And, of course, lowest order. And so, in view of this calculation, what we expect is that this I G mu nu in higher terms would be, in fact, let me just erase this to save space. It would be this term for the lowest term, and then it would be plus minus I G mu alpha over p squared, I pi 2 alpha beta minus I G beta nu over p squared. So that's how this quantity would play in correcting the ordinary propagator to order e to the fourth, say. And since pi is delta 1 and delta 2, this thing would be minus I G mu nu over p squared plus minus I over p squared delta 1 G mu nu plus delta 2 p mu p nu over p squared plus higher order terms. And so this thing then would be minus I, then that would be 1 plus delta 1 G mu nu plus delta 2 p mu p nu over just p squared plus I. All right, now this term we're not going to try to compute. This is a term that changes when you change the gauge, and when you couple this to conserved currents, the p mu is like a derivative, and the derivative of a conserved current vanishes. So this term is going to disappear. This is the one that we want. Delta 1 then is the correction to the photon propagator. It would be the correction then to the Coulomb force. And so what we'll be looking at then is pi 2 mu nu I e squared integral d4 k over 2 pi to the fourth minus 4 k mu k nu plus 2 g mu nu p minus k squared minus m squared, and then that is over p minus k squared minus m squared, epsilon k squared minus m squared plus I epsilon. Okay. Now, what do you think we do at this point? The what?
You're doing that finding sheet.
Yes, that's right. We're going to use a finding trick to use the same finding trick that we used last time to rewrite this. And with that trick, what we have is I e squared integral d fourth k over 2 pi to the 4th integral 0 to 1 dx. And then it's minus 4 mu k nu plus 2 g mu nu. Well, it's the same thing up here. P minus k squared minus m squared. And then the denominator is somewhat more complicated. It's k minus p 1 minus x squared plus p squared x 1 minus x minus m squared plus I epsilon, all that squared. Okay. Now, you can't shift unless the thing is a convergent integral, but we imagine that we know that what we're going to do is we're going to renormalize somehow and make the integral convergent. And so let's imagine that we renormalized, made it convergent, and shift. But that's complicated. So instead we're going to shift and then make the thing convergent. This is what everybody does. Even Weinberg does that. He has a footnote saying this isn't legit, but I'm going to do it anyway. All right. So we now do this shift. K mu goes to k mu plus p mu times 1 minus x. And then pi 2 mu nu of p then is I e squared integral d fourth k over 2 pi to the 4th integral 0 to 1 dx. Now we've got a humongous numerator, k mu plus p mu 1 minus x, k nu plus p nu 1 minus x, 2g mu nu times xp minus k squared minus m squared. And then the denominator, though, is a little bit simpler, because now it's k squared plus p squared x 1 minus x minus m squared plus I epsilon squared. In these loop diagrams, you have to keep the I epsilon. In the other things that we were doing, the tree level diagrams, you don't need to. Okay. All right, so let me see. Now, there are a lot of terms up here. Once again, a term that's p mu, p nu, when you put it between conserved currents, that's going to go away. In fact, any of the p nu ones are going to go away. And so what we're going to keep is the g mu nu and the k mu k nu. So we should call this pi hat, but instead we just go on as if nothing happened and write it this way. So 2I e squared d fourth k over 0 to 1 dx. And then, so the part we're interested in is minus 2 k mu k nu plus g mu nu k squared plus x squared p squared minus m squared. So everything else we're saying is going to go away and with conserved currents or be otherwise ignorable. And so what we have left then is k squared plus p squared x 1 minus x minus n squared plus I epsilon. Now this thing is squared. Okay, so this is in a nice form. On the other hand, we can see that it's potentially, it's quadratically divergent, and so we need to regulate this. Now, this business of regulation or renormalization and the technique that is used in gauge theories is one that was developed by 't Hooft and Veltman. In fact, they got the Nobel Prize for that. Because it was used to show that the standard model could be renormalized even if you had a Higgs field and spontaneous symmetry breaking and so forth. So I'm going to now go to Appendix B and say some things about dimensional regularization, although I'm not going to get through the whole thing, but I'll get through some of this. All right, so the first thing is that we have an integral d4 of k, let us say. And let's consider it of the form k squared minus delta plus I epsilon to some power. I guess let me call it capital N, just because I'm going to use little n for something else later. And we're going to be considering the case delta greater than 0. And with Schwarz's metric then, what we've got here is k squared minus delta plus I epsilon. This is going to be k0 squared minus k vector squared minus delta plus I epsilon. And so when that is 0, it's when k0 squared is equal to delta plus k vector squared minus I epsilon. And now if we take the square root and we put the cut on the negative real axis, then the roots are k0 equal to plus or minus the square root of delta plus, well, it's certainly that, but now if we put the cut on the negative real axis, then what we're doing is we're taking the square root of something that is positive and down here. And so the square root of that is, actually I think I put the cut on the positive real axis. The square root of that then is either something right here, positive and a little bit below the axis, or it's something over here. Okay, so we start out with this thing as minus I epsilon, and then taking the square root, we get either that or that. And so I actually put the cut on the positive real axis. Okay, so then this thing is plus or minus square root of delta plus k squared minus or plus I epsilon. Okay, so now let's look at the k0 plane. So then we've got a pole here and a pole there. And we're actually integrating K0 like this. Okay? But we imagine that this n is sufficiently big, and obviously this is a function that's analytic in K0. And even if we integrated d cubed k, it'd still be analytical in K0. So, and moreover, we can add a ghost contour out here. That is to say, a contour that's completely zero. Because you have 1 over k squared to the n, and think of n as 14. So that's 0, and then we come down the imaginary axis, and that's 0. So this integral along this contour, out, around, and down, of dk0, f of k0 is equal to 0. So the integral 0 to infinity dk0 of f of k0. So let me do it carefully. Plus the integral from I infinity to 0 and dk0, f of k0. This whole thing is 0, and we don't need to do this part because this is, as the radius goes to infinity, that's 0. So that means then, let me use this board because it's some black that's left. That means that the integral from 0 to infinity dk0 f of k0 is equal to the integral 0 to I infinity dk0 f of k0. And now if we say k0 on the imaginary axis is I k4, where k4 is real, this then is I integral 0 to infinity dk4 f of I k4. This thing is called a Wick rotation. Wick is, may still be alive, an Italian physicist came to the U.S. Lived here in the Second World War. He was at Columbia. Anyway, so that's the Wick rotation. We can do the same thing down here. We have this integral along here, and we can consider this contour going down and then around, and so it turns out that here I'll use this board, that the integral from minus infinity to 0, dk0 f of k0, is then I, the integral dk4 from 0 to infinity f. Well, that's what I wrote down, but I'm having second thoughts. Oh, this is minus infinity to 0. All right, let me do it in 2 steps, just to get it straight. It's the integral minus infinity to 0, dk0, f of k0. So that's this part, plus the integral from 0 to I to minus I infinity, dk0, f of k0. The sum of those two is 0. So this integral is equal to minus the integrals from 0 to minus I infinity dk0 f of k0. And now let me just keep this straight. So this is that, 0, so that's minus that. And let's see, what do I want to get? I want to get, right, okay. And so that is the same thing as the integral minus I dk4 f of I k4, and now k4 is going from 0 to minus infinity. Right, okay. So that's the way it looks. And so consequently, this whole thing then can be, we can turn that integral into this integral. And so then this is what we get is, we're integrating, let's see, 0 to, I want to get my eyes straight. Okay, I. Yeah, okay. If we switch from, if we can absorb the minus sign, and then we can go from minus infinity to 0. And now we have plus I. Okay. So the whole thing then is an integral minus infinity to plus infinity, an overall factor of I, dk4 dqk, f of ik4k. So that's what we've got. And the ik4 means then that everything here is negative. And we have an extra I. Okay. So what is this thing then? It's the integral d4 k over 2 pi to the 4th. 1 over, let us say, k squared minus delta plus I epsilon to the n is equal to then I integral, let us say, we call that d4 k Euclidean, where now this thing is 1 over minus k Euclidean squared minus delta, and the I epsilon we don't need anymore. And so equivalently that's minus 1 to the capital N I integral d4 k Euclidean over 2 pi to the 4th 1 over k Euclidean squared plus delta raised to the power n. And k Euclidean, of course, is just k1 squared plus k2 squared plus k3 squared plus k4 squared. Okay. So this is an integral where everything is, so this whole thing is called the Wick rotation, and now we don't have any poles, we're just integrating over what's called Euclidean force space. Euclidean because it's this nice metric that's somewhat simple. All right, now this is a good time to ask questions because
so that means
because I have candy.
that means we are going back to statistical mechanics.
In some sense, yeah. Quantum field theory in Euclidean space is like statistical mechanics.
Through the Wick rotation.
Except that statistical mechanics is in 3 dimensions and quantum field theory is in 4 dimensions. Let me just take another candy in case someone else asks a question.
took the I epsilon out of the root, when you said you chose the positive root, put the K0 there, at the bottom of the board.
Yeah, what we've got, we're taking the square root of something that's positive and then a little bit below the real axis. Okay. So, one way is, suppose you have this number, minus plus I, very tiny number. You square it, you get plus, and then this guy goes down. In other words, the way you do that with a complex number is you just, rotate around. So that's one. But another one is just that this guy is sitting right under here, and and you square it so it gets longer and then goes down a little bit. So, in other words, x e to the minus I epsilon squared is x squared e to the minus 2I epsilon. So that's why this one becomes that one. On the other hand, minus x e to the I pi minus I epsilon, that's this point. Okay? Oh, no, there's no minus sign here, because I've got the minus sign in the I pi. This thing squared is x squared e to the 2 pi I is 1, e to the minus 2I epsilon, which is the same number. So it's this thing here. So that's how that works. Any other questions? In other words, it's just complex variable theory. Let's say, I should have put that as an example in my book instead of having Plana column, which is so much more complicated. Because I had other examples, closed countries, but this one I should have included. Okay, so this is what we get. And now the question is, well, how do we do integrals like this? And obviously, once you get something that's just k squared, and you have then integral over all space, what you can do is you can go to spherical coordinates. But when you go to spherical coordinates, you need to know the area of a sphere in 4 dimensions. And there's a trick that was introduced by Pascal when he was alive, a long time ago. And by the way, speaking of a long time ago, astronomers just found out that the earliest stars formed about 550 million years after the Big Bang. And these were very large stars, because about 1,000 times the size of the mass of the sun, because smaller stars, smaller clouds of hydrogen and helium couldn't condense quickly enough, couldn't condense and form stars. And the reason is that to get a small star, you need a cloud that has elements that can cool more easily. And hydrogen and helium can't cool as easily as a cloud that has oxygen and nitrogen and iron and so forth. And so small stars form today, but only big stars formed in the first generation. I mean, I'm calling it the first generation. Obviously, the astronomers would never use language that simple. They call it the 4th generation or something. And, they all talk Pascal and his trick. Imagine we are in n dimensions. So dx1 e to the minus x1 squared, dx2 e to the minus x2 squared, all from minus infinity to plus infinity. Okay, so what's this? Well, it's very simple. This, of course, is integral minus infinity to plus infinity e to the minus x squared dx raised to the power n. That's why I use capital N over there. This is square root of pi. So this is square root of pi to the n, or pi to the n over 2. On the other hand, this also is dnx e to the minus sum of xi squared I equals 1 to n. And so this is integral dnx e to the minus r squared, where r is the distance of the point from the origin. And so this thing is, well, it's clearly dr 0 to infinity, r to the n minus 1 e to the minus r squared times something. And that something is the normalized surface area of the sphere in, well, n minus 1. It's the n minus, it's called the n minus 1 sphere, but it's the sphere in n dimensions. On the other hand, this integral is a well-known integral. This is, in fact, therefore, Cn minus 1, it's 1/2 gamma of n over 2. That's what that actually is. Gamma functions in chapter 4. Okay, so what do we know? We know then what this Cn is. Cn minus 1. Cn, oh my God, look at this. I went to the trouble of using capital N for the other thing and then switched to capital N. All right, Cn minus 1 then is what? It's pi to the n over 2 times 2 divided by gamma of n over 2. And so that means that the area of a sphere, the area of the n minus 1 sphere then is 2 pi to the n over 2 divided by gamma n over 2 r to the n minus 1. That's the area of the sphere in n dimensions. And so in particular, A3 is 2 pi squared, and gamma of 2 is just, well, all right, let me write it as gamma of 2. And gamma of an integer is n minus 1 factorial, and so that's just 1. And this is, of course, r cubed. And so this is just 2 pi squared r cubed. Okay, so we can then try to make some sense out of this integral. This integral then is minus 1 to the capital N, I, and now it's an integral, what? Well, it's k cubed times this C3, which is 2 pi squared. So it's k cubed 2 pi squared dk 0 to infinity divided by 2 pi to the 4th. And now we have 1 over k squared plus delta to the power n. Okay. If we go to the case n equals 3, smallest integer for which this is actually convergent. For n equals 2, we have k cubed over k to the 4th, so that's a log divergence. So we go to k cubed over k to the 6th. That's finite. And so what we have then is n is 3. So this is minus I, 2 pi squared over 2 pi to the 4th. And now integral 0 to infinity dk, k cubed over k squared plus delta cubed. So this cubed is because we're in 4 dimensions. This cubed is because we chose capital N equal to 3. And, well, 2 to the 4th is 4 squared, so that's 16. And so this is minus I over 8 pi squared. And now I use Mathematica to do the integral, 1 over 4 delta. And so this is minus I over 32 pi squared delta. Okay. So that's an example of the sort of, that's an example of the Wick rotation and also of how to compute integrals like this. Now, of course, what we've got is we've got to deal with the case when n is equal to 2, and occasionally when n is equal to 1. And for n equals 2, there's a reasonable thing that we can do. We can say, well, we can continue. This was the idea of the Dutchman, Veltman and Hooft. And it's unfortunate because they, we have here d to the d, which is kind of ugly notation. But we imagine doing this integral in d dimensions. Okay. And so we have 1 over k squared minus delta plus I epsilon squared, say. Well, when does this converge? Well, this will converge if p is less than 4. Because, of course, that means that we've actually given a meaning to the integral in 3.9 dimensions, let us say. On the other hand, we have just gone through a calculus here which tells us what that might be. In other words, the integral of something in an arbitrary number of dimensions, once we've gone to something to spherical coordinates, what would it be? Well, so let's do this in d minus 4 dimensions, in d dimensions. Well, this thing would be an integral 0 to infinity. It would be k to the d minus 1, right? It would be the area of the sphere in d dimensions. Now let's get this straight. D dimensions. So it's the d minus 1 thing here. So it's 2 pi to the d over 2, right? Divided by gamma to the d over 2. Okay? And we also have, oh, it's not 2 pi to the 4th, it's 2 pi to the d. so we've got that part, and of course, dk, which I should have written there, but there's no room. And then we have 1 over k squared minus delta plus I epsilon squared. And so now we have to ask Mathematica to do that integral so in other words, the dk integral is fairly simple. It's just that k has is a real power here. Does anybody have a laptop open? No. Okay. Actually, if you look at, here, let me just go to this. Let's just see if we can find what this integral is. All right, it's well, Schwartz here has a formula for something more complicated, but let's just say that if you're sitting in front of a computer with Mathematica, or you have a sufficiently large table of integrals, you can do this integral. It's something involving gamma functions. We also have a gamma function there, so it's some known expression in terms of d and gammas and so forth. And the nice thing about this is called dimensional regularization. Regularization means just it's some method of making infinite quantities finite by changing what it is that you're doing. Dimensional, of course, means that we've changed the dimension from 4 to some continuous version. In fact, some people use the term analytic continuation and imagine that the D is actually complex. So far, I haven't needed to do that. The advantage of dimensional regularization is that if you have a gauge theory, you don't break gauge invariance doing this, and even in the non-abelian case. And so you have a method of regularization which is gauge invariant. And before dimensional regularization, people didn't really know how to renormalize in general non-abelian gauge theories, especially with spontaneous symmetry breaking. And they knew how to do quantum electrodynamics. Schwinger and Feynman worked that out, and Tominaga in Japan. But the non-abelian case was uncertain. Now, as I said to you at the beginning of the lecture, though, I think the really consistent way to do all of this stuff is to say, well, we're going to define certain amplitude, we're going to measure certain things, and then we're going to use the theory to compute how those things would be at different values of energy or momentum or whatever. And it's probably true that it's possible to carry that out in such a way that you don't have any infinite quantities at all. And I think that would be a much nicer way of doing quantum field theory. As far as I know, nobody's carried that through. because I don't know everything. So it could be that somebody's written a book on renormalization where they've done exactly what I'm talking about and slaved over it for, spent 10 years writing the book, correcting the typos, and nobody's paid any attention, which is kind of sad. So I don't know if that's possible. All right, I guess we can stop now. I'm thinking of going to that lecture in humanities tomorrow at 2 o'clock.